briefly, we can construct a slope graph from a given graph if we take a series of points along the given graph and draw tangent lines. Each tangent line is at some point of the graph that has an x-coordinate, so we call the point at which the line is tangent to the graph the point of tangency. And now we have the fact that each point of tangency is associated with an x-coordinate, so wherever x is, if the point of tangency is here, x is directly below it, and that x value is the x value at the point of tangency. So we have tangent line, tangent line, tangent line, tangent line. We construct a series of triangles between points of the tangent of each tangent line. Okay, for each tangent line we construct a triangle that goes from one point to the other with its legs, a right triangle with its legs parallel to the y and x axes. So we've constructed such a triangle here, we've constructed one here, we've constructed one here, and it doesn't matter whether the triangle goes above or below the graph. Above the graph you would have the same rise and the same run, so you would have the same slope. And here's another one. Now, one characteristic of each of these is the run is constructed to be the same for all 4 points, for all 4 tangent lines, so that we can construct a slope graph. Again, slope versus x, the slope of the tangent line versus the x-coordinate of the point of tangency. We don't have to calculate the slopes in order to construct this graph because we don't need we're constructing an unscaled graph here. We just want to know the general behavior of this graph, the general nature of this graph. We're trying to infer something about the general nature of the graph. So whatever the slope is here is going to be the rise divided by the run. Whatever the slope is here is going to be this rise divided by the run. The run is the same, so if we simply represent the length of the rise here by an x, and the length of the rise here, well, by an x, that's ambiguous, by a point, okay. The y-coordinate of this point stands for the rise of this graph. The y-coordinate of this point stands for the rise of this graph. The y-coordinate of this point stands for the rise of this graph. The y-coordinate here is the rise of this graph. Then we can say, if we scale this properly, then these y-coordinates represent the slopes. I'm not going to go into too much detail about that, but it's so. We just have to put the right scale on it to make it so. Since there's no scale in this graph, there's no scale in this graph, so this could represent the slopes. Okay, so in any case, we have this slope graph. Now you can see the other video, the longer video, for a more detailed demonstration of what we're doing here. When we did this, we found that these slopes appeared to just about double. From here to here it doubles, from here to here it doubles, from here to here it doubles. So that these slopes are all double, but these distances between the points of the x values of the points of tangency are not equal to the doubling displacement of the original graph. So, is it conceivable that this graph is in fact exponential with a different doubling displacement different from this graph? Or is it really exponential with the same doubling displacement and we just didn't construct it quite accurately enough? Or is it not even exponential? Because these points were not all that uniformly separated. The x-coordinate of this point, this point, this point, and this point don't all differ by the same amount. So very questionable whether this is exponential. Now we can do the same thing with a graph of, let's say, the 5/2 power function, the orange graph here. I've sketched tangent lines, 3 tangent lines, and then I've sketched triangles with equal runs, equal run here, equal run here, equal run here, and representing the slopes then by, let's represent the behavior of the slopes just by the rises, since the runs are the same. And we find that the graph ends up looking something like this. This is a slope graph, slope versus x. Slope at the point of tangency versus the x-coordinate of the point of tangency. This looks like it could be a power function curve. Matter of fact, it looks a lot like the 3/2 power function curve. Not necessarily so. Well, you could test this graph to see, set up a set of x's that double. This one appears to about double this one, but if we wanted to double this one, we'd have to come out to about here. So we could look at this point, and this point. Okay, between here and here, does y change by the same factor as it does between here and here? If so, there's a fair indication that this is a power function. Is the factor 3/2? If it is, then this would be the 3/2 power function. It's something to be easy to check out.